In this lesson, we'll go over an ANOVA example that relates to completely randomized designs. So we're going to go back to the highway paint example, and if you remember this example, our goal was to compare the reflectivity measurements of the 3 new paints to one that was currently being used on the highway. So we have a total of 4 paints, and the implementation of this experiment was 16 similar highway sections are selected, and each type of paint is randomly applied to 4 of those sections. So we've set this out as a balanced, completely randomized design. You just randomly pick out which sections of highway receive the treatment of the paints, and you're going to see each of the paints the same number of times. So we have 16 total experimental units. The data is here for you. You can see the different types of paint along with that decrease in the percentage of reflectivity. And here are the mean of each of those measurements. So looking at it, it looks like there could be a difference across the means, but we'll need ANOVA to be able to take into account also the variability or the background noise. Just looking at this with some of the notation that we've used before, remember T is our number of treatments. So here we have the 4 types of paint, which we'll call P1 through P4. There's 4 replications. So replications are the number of times you see each treatment. It's balanced here. So we see each type of paint on 4 sections of the highway for a total of 16 experimental units. And just recall some of our notation, the Y double dot bar, that's your overall mean, right? So if you sum all of these up and divide by the 16, or you take each mean and divide by 4, we get a total of 25 as our overall decrease in reflectivity. So the first step of ANOVA is to set up the hypotheses. And these first 3 options here are all valid ways of writing the one-way ANOVA CRD hypothesis. So under the null, you could say all the means are the same versus at least one mean differs. You could also do it in terms of the effects model. So all of the treatment effects are 0. Again, saying there's no difference across groups versus at least one of those is different. And then I'm perfectly happy if you just want to write it in terms of the context of the problem. So you could have here that the paint has no effect versus the paint has an effect, right? So under the null, we say there's nothing there. And under the alternative, we say that the treatment has an effect. After we do that, we need to compute the test statistic. So on this next slide, I show you how to compute the test statistic using the more computational form of the sums of squares. Now, I will tell you that in this orange box, it says you will not be asked to calculate these sums of squares by hand for a test or for a homework assignment. We're going to rely on software to calculate these, but sometimes people like to look at how they're calculated by hand to kind of get an idea. So you'll notice that I use the sums of squares for the between group. I calculated the total sums of squares, and then we use the property that the additivity, that if you take the sums of squares total plus the sums of squares error, the sums of squares treatment plus the sums of squares error, you get the total sums of squares. Once I get my sums of squares, I can then calculate my F statistic. Recall that the top here this is going to be your mean square. Sorry about that. This is going to be the mean square for the treatment. And this is going to be the mean square for the error. And when we calculate that, we get 0.98. Now that's a very small F statistic. We talked in a previous lecture about how 1 is kind of your cutoff. 1 says there's really no difference between the groups. This is even smaller than 1, which can happen again with the random variability. So I'm not expecting to see significance here. Now you'll notice that one way of doing the rejection rule, and we'll do this here, but this is probably the last time we'll do it this way, is you could go to the F distribution and you would figure out a cutoff on that F distribution that would give you an idea about where you would expect for an F test that has 3 degrees of freedom for the numerator and 12 degrees of freedom for the denominator. You would figure out a value of the F distribution where this area here is 0.05 or whatever your alpha level is for the cutoff. And then if your F statistic is beyond that cutoff, which for this particular case was 3.49, then you would reject the null hypothesis. So since our F statistic was 0.98, which is less than that cutoff, we're saying it's not extreme enough. It doesn't seem like there's a difference across the groups. So we're going to fail to reject H naught and conclude that there's no reason to believe that paint have different percentage decreases in reflectivity, right? There's no reason to believe the alternative hypothesis. Again, when using statistics in practice, we rarely look at statistical tables to figure out these cutoffs. Most of the time we use the p-value. So what the p-value is going to do is it's going to plot your 0.98 on here. It's going to plot your 0.98. And then it's going to look at the area to the right of that. So it's going to give you all of that area, and that's your p-value. That value is going to be bigger than 0.05, so we're going to make the same conclusion. We're going to fail to reject the null hypothesis. And you can see that here. Now here's the ANOVA table, and I'm going to show you in the next lecture how to get those ANOVA results in JUMP. But my conclusion here, again, from the F statistic was we fail to reject the null hypothesis. But if we looked at the p-value that's related to that, so this is a much better drawing than what you guys saw on the last slide, this area is very large, right? So it's much higher than 0.05, so we're going to fail to reject the null and concludes there's no reason to believe that paint have different percentage decreases in reflectivity. So just to summarize, if we summarize, the first step is to state your hypotheses. The next step is to compute your F-stat and p-value. And again, you can do that with software. And then your third step is the conclusion. And so if your p-value is less than or equal to alpha, okay, and I'll say alpha usually is 0.05, then you're going to reject H naught. That's where you have statistical significance. And then if your p-value is greater than alpha, you're going to fail to reject H naught. Okay, notice I'm not saying accept H naught. I'm just saying there's not enough evidence to conclude to conclude the alternative hypothesis. So that's how you do the CRD analysis. If you recall from Stat 5615, the one-way ANOVA analysis, the exact same thing. We're doing it here. We're just now talking about it in the context that we've designed this experiment that's a completely randomized design.